eventually going to get to sample examples of creating multiple like one-dimensional maps for these higher dimensional kind of objects or spaces?
Yeah, absolutely. So one of the things you can even see in the homework, right, is that what do we do in the homework? I think it's actually next week's homework, but what's the idea, right? Is that instead of just looking at a single plane for the Rosler system, you look at different planes, each of which have some sort of symmetry to them, right? And each of those give you different Poincare sections. So like one of them gives you a section like this, and one of them gives you a section like this, right? And another gives you a section like, I think it's like something like this.
I mean, I guess what I'm getting at is, and it
Yeah.
wasn't clear at all what I was getting at. Are these Poincare sections always codimension 1? I mean, because if you have like a high dimensional system, does it make sense to make a Poincare section of a Poincare section, for instance?
Oh, I see what you're saying. Right. So codimension 1 is very particular, right? The reason we're choosing codimension 1 is because what effectively, so going back to this idea, and I didn't explain this well. So we're trying to capture something about our system by removing some symmetry inherent in that system. So initially, that symmetry that we were trying to remove, that we invested all this time into the Poincare section, was time, right? Because I don't care what happens along an orbit. I want to care about the dynamics transversal to that orbit. Okay? Now, theoretically, if your system had many symmetries, right, we could try and understand lower dimensional objects as sort of passing through these symmetries, right? We could try to understand something about how these systems behave according to that. But if all we're given is, that we know that these things exist along certain orbits, and we want to make sure that the recurrence actually hits these things over and over again, sort of the only symmetry we have to deal with initially is time. Right. So it's
that's super interesting. So the codimension is related to the number of symmetries in the the action or whatever. Okay.
Yes.
Cool. Thank you.
Yeah. Any other questions?
I just have a quick question if you have the time.
Yeah, absolutely.
Could you further explain what you mean when you say that you don't lose any information about the flow using the Poincaré section method?
Yeah, so this is something that's a little bit it bothers me a little bit. So it is true, right, that like if I were to let's limit this to 2 dimensions, okay? If I were to give you a map from 1D to 1D, right? And I were to say, this is the Poincaré section, okay? This is the map from xn to xn plus 1. There is no way from this map for you to tell me what the flow is, right? There's no way. You can't do it, right? Because theoretically,
that's what has me confused as well.
Yeah, exactly. But here's the thing. If you fix the flow underneath, so if you don't forget the dynamical system that you're working with, right, you are capturing all of the orbits which pass through this Poincaré section. And assuming we're limiting ourselves to understanding just the non-wandering orbits, that's going to be, and we choose our Poincare section well, right? That's going to be every single orbit that we care about. So you are truly getting like an accounting of all possible orbits by looking at the Poincaré section. So it's not true that every Poincaré section inherently gives you a particular flow, right? But it is true that given a Poincaré section, you don't lose any information about the flow, right? As long as you still have the underlying dynamics, you could always just pick a point on your Poincaré section and continue integrating to get all of the points in between.
Okay, that makes sense. So it's the Poincaré section, provided that you understand, you haven't forgotten your dynamical system. This
Exactly.
is just a good way of accounting for, oh, okay, yeah. That makes more sense. Thank you.
Yeah, it's a weird notion. It bothered me a lot. Still bothers me a lot. But, you know, as long as you understand that, like, what we're really interested in is as long as you have the underlying dynamical model, as long as you have a single point on your orbit, you have the orbit. This is a weird notion, but it's true. As long as you have a single point on your orbit, you have the whole thing.
Yep, that makes sense.
Okay. Any other questions about one-dimensional? Oh, and I'm sorry, I didn't write this down, but this procedure that I drew here that's used to sort of help visualize one-dimensional objects is called cobwebbing. We won't see it a ton, as far as I understand, because it's not, you know, whatever. But if you ever want to sort of get an intuition as to like what the professor was talking about when he was talking about this like baking motion, where this strong downward thing corresponds to sort of objects getting mixed around, I would play around with some cobwebbing diagrams where you have sort of a deep downward thing. That's going to really help build that intuition as to what's happening. Any other questions, comments, angry replies?
So people, you know, I love Chris's presentation. Maybe we should fire the professor and have Chris take over, but this is the idea, you know, we have one person just read carefully, think about the material for the particular online Chaos Book lecture, and critically discuss it, you know, with your own point of view and with your own angle. And, you know, if you discuss in a class, I think you learn much more than just reading the book. So, you know, that's what makes a live course more fun, in my opinion. The other thing I want to remind you, I want to remind you of what happened in the Korean War. And it might happen to you. So far, I have only one person who has volunteered without nudging from the central committee. So what will happen very soon, you'll find your list on the schedule of the course, what section you're doing. I will do this the way that, you know, Chairman Mao did it. So, but you have a chance if you volunteer for something you actually want to present. Just let me know and I'll include it. And, you know, we can stop earlier. We don't have to go to full class if there is no interest in discussion, because there's lots of time already being used on reading the material and maybe watching other videos. So that's perfectly okay. And if you want to discuss anything else, not necessarily Poincaré sections, maps, cobwebs, you know, this is a good forum to do it.
Yeah, so just to address one more thing, there was a question in the chat about why these maps are continuous. And so maybe I want to give some intuition as to like where that comes from. You know, when we're looking for where these maps sort of exist, right? We have some vector field which associates this flow, right? This time t flow that we have according to our system. And that's given from a specific x naught, right? And then we want to know where you have some level curve, right? And so you're trying to find some value where this is equal to 0, okay? So this is really what it means to intersect, for the orbit to intersect with the Poincaré section. Now, why did I do this? Why did I write this like this? Well, what do we have here then? We have a map, call this f of t, from R to R, right? Given by this whole thing of you pick the time, you flow according to that time along this orbit, and then you check the value of this level curve. And if it's equal to 0, then you're at the Poincare section. So now we have something which is differentiable in T and differentiable in T. And this transversality condition actually tells us that there's a non-degeneracy going on. Because if, for instance, I take the derivative of this with respect to T, what do I get? I get U, get the gradient of U evaluated at the point, dotted with the derivative with respect to time of this flow map. Okay. And what is that? That's the gradient of U evaluated at the flow point times the velocity field, again, evaluated at the flow point. And we said that this was not equal to 0 by construction. Okay. So you have a differentiable function which has a non-zero inverse. And so you can apply the inverse function theorem. So with this setup, not only are these maps continuous, you can actually show that they're locally differentiable. And you really do get this like true inverse map, which is being encoded by this transversality condition. You can also think about that as like a consequence of sort of the robustness of our intersection with the flow. So sorry, yeah, that was just a little digression because of the question. Anything else?
I have a few remarks.
Yeah.
You know, somebody wants to ask a question.
Oh, sorry. There.
You know, I come last if anybody wants to ask a question. But
I mean, maybe asking too much about physics intuition. I'm not quite sure what you mean by that. Are you asking like the physics intuition behind why the map is continuous? Is that your question?
Yeah, that appears to be his question.
Okay, cool. So the physics intuition behind it is that, what's the idea? So these flows take globs, right? And they move them around and then slam them into other globs, okay? So there's some amount that these globs get stretched as they flow around the surface and eventually hit back into the Poincare section, okay? And the fact that the globs don't blow up in between, that they don't sort of become, you don't have things that are super small, which then blow up into massive portions on your Poincare section. That is what is giving you the continuity of these Poincare sections. The fact that there's some sort of limited amount of explosion that happens between those 2 points. That would be my best explanation.
Can I say something?
Yeah, for sure.
Is the continuity of the Poincare section a consequence of the continuity of the vector field?
Yes. Absolutely. So you can't expect the Poincare, so you can't expect the Poincare section in any way to be better behaved than the vector field. Sometimes you get lucky and you get dumb luck, and there are some things that if there's some issue with your vector field way far away that's not involved in the wandering, that's involved in like the wandering dynamics, but it's not involved in the recurrent dynamics, then theoretically you could have like a better behaved Poincare map than like a full vector field. But that's just totally relying on dumb luck. These structures are really coming from the vector field, and so you can't expect them to be any better than you started with.
these ideas seem very nice because you can visualize what happens in three-dimensional flow, like Lorenz and Rossler, the one we'll work out. So, you know, they make lots of sense. Now, if you go to higher dimension, it's hard to understand what codimension in 1000 dimension Poincare section is 999 dimensional. Still, you know, what it means, it's full of points rather than lines, because lines are all transfers to it. So you actually get much better understanding and visualization of flows in sections than you ever get by looking at the flows themselves, because they're very busy and complicated. Now, one thing that is not obvious at all is that, and it's probably almost never true, is that you can cook up a Poincaré section that cuts the entire thing. In mathematics, that's called cross-section. In physics, that's a very unfortunate use of the word. That can almost never be done. There are kind of singularities and this and that, and the manifolds are not manifolds, the orbit folds, etc. So it's a practical issue, can I work out some neighborhood? And usually you need to produce several Poincaré sections to really cover all the stuff you care about. But it's a dark art. Some people do it better, some people do it worse. You have to have some intuition about flow, which is hard to do. And nobody tells you how to do it. Different people, different papers produce same flow, different Poincaré sections. The third remark is that actually, by the time we get in the second part of this course, we'll just throw all this scaffolding away. I mean, just a human way to understand geometry of the flow. But only information you will actually, the flow are orbits, meaning the infinite time trajectories. And if they're periodic, they're even finite, you can compute them. And if you understand all the orbits of the system, so the real dynamical space you have to work in is not the points where you started in your original space, each point having a spaghetti going through it. No, you have to count the looped spaghetti, the things that are recurrent. It's there where invariant information is, everything you can, but that's maybe a too sophisticated remark at this end. But that's why the course is not done in 2 weeks, but in a semester, because we'll have to come back to it over and over again. So what in other branches of physics, like particle physics, you do, at some point you learn that you don't actually care whether the machine is in Shenzhen or CERN and how it's oriented. You only care about the masses of the particles, and you only care about their spins, so invariant properties. Technically, that's called Casimir operators and invariants. You only care about values of things that everybody can agree on, they're intrinsic to the problem. So in dynamical systems, it also happens, but it's not as simple as in particle physics. In particle physics, you have linear spaces and groups and Casimir invariants on them. Things like kinetic energy squared sum over everything is a number that everybody agrees on in all representations of a physical system. Here it's much fancier because there's this topology and things are entangled, and you have to count infinitely many orbits, because in chaos you have infinitely many things you have to take care of, and you have to put them together. And that's what the zeta functions and things like that will do, how you collect all this infinite invariant information that doesn't depend how clever you are in doing your Poincaré section. But you're working on your problem in your PhD thesis, you'll find Poincaré section immensely useful, because that gives you intuition. You can navigate it as a human.
What about, say, the Lorenz Attractor with two separate butterfly wings on which two neighboring points can end up? Wouldn't this give a discontinuous map? Or are you saying a continuous line between neighboring points would make? Oh, no, yeah. So okay, so let's talk about the Lorenz Attractor really quickly. So the Lorenz Attractor is a strange attractor, and in many ways you can think about it as the omega limit set of the given dynamical system. So what does that actually mean? That means that the dynamics that are left over once an infinite amount of time has passed. So all of the recurrent stuff is kept, and the only things we're considering are sort of variant things. The Lorenz butterfly wings are not in and of themselves a Poincaré section. So what you would imagine is that, let's say I have the two butterfly wings. Okay, two butterfly wings. And it goes away. That's a terrible picture, but whatever. I can't, Anyways, so you pick a given Poincaré section. And all I'm saying when I'm saying it's continuous, let's give this an orientation, is that if I can pick a small enough block on this section, it'll evolve through all of this and go through all these dynamics and pass near this Lorenz Attractor and spend a bunch of time near it and all this sort of stuff. And it'll come back and it's only going to grow a certain amount. So I can control how much it's grown over that whole time. That's all continuity is saying.
Does this picture help you visualize Poincaré's section of Lorenz flow?
Well, I think that's all I have for today, y'all. So thanks for hanging out. I hope you got something out of it.